has been staying here for this year at CITA. It is PhD at Caltech before going for postdoc at UC, and then back at Caltech, and then at KITP. And then in 2003 moved as a professor at MIT, where he has been since then. Today he's going to talk to us about orbital resonances and their impact on binary spiral.
Okay, thanks. This is some work which has very personal importance to me. This is the first thing I've managed to finish since my daughter was born last year. And so it's good to be able to put a bow on something and realize I can be a scientist again, not just a daddy. Less jokingly, I'm going to talk to you about the fact that it's one of those things you kind of go, why didn't we notice this before? Because I'm going to talk about some resonance effects that we see that are sort of generic to binary inspiral. They're most important when systems have large mass ratio. And the effect I'm going to talk about should be sort of hidden in all the analyses that people have done to date. But they are cleanest when the mass ratio is large. And as I'm going to show, based on some of the analyses we've done, they have potentially surprisingly important impact. So when I start doing any kind of, a lot of my research is on looking at sort of clean limits of the two-body problem in general relativity. I always like to remind people that there really is no such thing as a two-body problem in general relativity per se. General relativity is not a theory of bodies so much as a theory of spacetimes. And so when we talk about the two-body problem in GR, we're really talking about a one space-time problem in which we can sort of identify unambiguously two separated bodies at some limits and then ask what happens after that. So the way we do things in numerical relativity is we start with some initial configuration that unambiguously looks like two bodies, two neutron stars, and two black holes, or something like that. We enforce the Einstein field equations and our conservation equations, and spend 30 years writing computer codes for this, put it onto a computer, hit a button, math happens, and that tells us how the space-time evolves, and we get from that what the dynamics of the bodies that are described by this space-time, how they behave. And a lot of great things happen from this. To really make sense of the issues I'm going to talk about today, we found it most useful to go to a large mass ratio limit, which actually allows us to think about the notion of bodies a little bit more sensibly in an easier way. I'm particularly going to talk about something where if you think about the astrophysics, we're really talking more about the extreme mass ratio bodies, where your inspiraling little guy might be sort of the mass of a star, but we want it to be a compact object so that it's not highly disrupted by the larger black hole. Being captured onto a strong field orbit of sort of a million solar mass black hole. This is, in fact, an important source for space-based gravitational wave detectors, should the various national agencies ever figure out a way to fund and launch one. But for, I think, more general purposes, I think this is it's useful to think of this as just a living case of the general two-body problem, where we can look at things in a particularly clean limit and perhaps identify phenomena that may be harder to see in the more general case. I'm going to use the extreme mass ratio in spirals to frame a lot of my discussion, but I'd like to have in the back of my head that there's some things we're finding in this that may be more general, and maybe fun to look for these in more general analyses of binaries. So in this particular case, we still analyze our system the same way we did it in the general case. Okay, we're going to imagine that we just have some initial configuration and we enforce the rules of general relativity. My zeroth order analysis of this system is I'm just going to say that the little body is moving on the space-time of the big body. When I require that the conservation laws be held, what I find is that the little body has motion that's governed by the Geodesic equation of general relativity. And this is just saying that at zeroth order in the mass of the small body, it just follows the geodesic of the background of space-time, which you can file in the journal Duh. I mean, that is what we learn in all general relativity textbooks, but this is sort of a neat way to see it actually come out. If I now, this is where it gets more complicated. This small body doesn't just ride on the space-time of the big black hole. It changes that space-time a little bit. Okay? It's going to change things. It's going to dimple the space-time in some sense. And if I repeat this analysis, I enforce the conservation laws in a more general space-time that looks like the big black hole plus the change to the little guy, I get something that looks like a Geodesic equation supplemented by a forcing term. What this forcing term does is push the body off of your naive notion of a geodesic. And when one analyzes this carefully, you find that it's got dissipative effects that drive it in spiral. In other words, it encapsulates the fact that gravitational waves carry energy and angular momentum from the system. And there are also conservative effects, which I will talk about briefly a little bit later in the talk. When you actually work through this and you compute what this self-interaction term is, it's instantaneously small. Okay, so this thing, if every one of these terms is of order 1 in some system of units, then this thing is a factor of the mass ratio smaller than this. Which is one reason we can get away with neglecting it for many analyses. However, the effects due to this thing accumulate. Okay, so there's a secular accumulation of these effects, and you have to carefully model what's going on with this if you want to make an accurate model of how this system evolves. In particular, things like the actual inspiral itself are due to this, and we know that they accumulate and can lead to very large changes in the system. So I'm going to get a little bit technical for a few moments and put together a framework where I can sensibly look at the key things I want to look at here. I'm going to take the equations of motion that are derived from this thing, essentially this force geodesic equation, and I'm going to recast them in an action angle variable formalism. So my Q's here are essentially generalized angles that describe the position of my body in space-time. So for instance, QR is an angle that varies from 0 to 2 pi. And as it goes from 0 to pi, an object in an eccentric orbit might go from periapsis to apoapsis, and then from 2 pi it goes back to periapsis again. Similar angles describe the motions in my two angular coordinates and in time. And I have a bunch of quantities that, if I just look at motion in the background, are conserved. Energy and angular momentum we're all familiar with. There's a quantity called the Carter constant, which separates the motion for Kerr black holes. Roughly speaking, it's the other two components of the angular momentum, though not quite. So when one takes that sort of force geodesic equation, you can write the system and write in this formalism, you get a set of equations that look like this, where I have bits here that come in proportional to the mass ratio. These are essentially what that forcing term turns into.
So Scott,
yes?
Just to get an idea what Q is, if I have a purely Keplerian potential, what would Q be in that case?
Q in that case would be, so QR would be something like an anomaly angle.
No, not Q.
Oh, I'm sorry, this Q, capital Q.
Yeah.
It would be the square root, not even the square root, it would be Lx squared plus Ly squared. Okay, so if you have a spherically symmetric potential, it really is just the rest of the angular momentum.
So it's not related to the lunge.
No, it's not. It's not. Yeah, because actually in a black hole spacetime, the Runge length vector isn't conserved.
Yeah.
Right, because you can probably do something where in a weak field limit you can relate it to it somehow. I don't know any others that have actually done the exercise, although it's occurred to me that might be a fun homework assignment for my jar class someday. Anyhow, so yeah, so that's a good question. This is, in the spherically symmetric limit, this is the rest of the angular momentum components, and it's similar to that using Kerr. Okay, so I want to take these equations of motion and look at them again just order by order. If I look at things independent of the mass ratio, what these equations tell me is that my conserved quantities are conserved. They don't change as I evolve with respect to my time parameter. And my angles all accumulate at a rate that's set by their associated frequency. This is just a restatement of the geodesic equation, saying that I have closed motion with all of my conserved quantities being conserved. I go through this in some detail because these are going to be useful for background of what I'm going to discuss here. Because when we talk about motion of Kerr black holes, the background motion is very simple to characterize almost completely analytically. So if I give you these three constants, the energy, the angular momentum, and the Carter constant, that maps into a particular orbital geometry that fills a torus in the region near the black hole. Your orbit is confined to within some minimum radius and some maximum radius. There's some minimum theta angle, some maximum theta angle, and this whole thing is then axially symmetric around the spin axis of the black hole. And associated with the motion of this body in this torus, there are three completely well-characterized periods. I'm just going to write them as frequencies. So there's an omega r associated with the time scale to go from r min to r max and back, and omega theta associated with the time scale to oscillate in the theta direction, and omega phi associated with the time scale to go around the spin axis. And each orbital geometry modulo a couple interesting degeneracies that look like they're curiosities but are kind of cute. Every orbital geometry essentially picks out some unique triple of these frequencies. We look at how they behave as a function of orbital parameters. What we see is that at very large radius orbits, they asymptote to Kepler's law, as we would expect. And as we get into the strong field, they vary quite a bit. The radial frequency tends to hit some kind of a maximum and turn over. then the theta and phi frequencies generally grow all the way in until other things happen.
So where is the innermost stable orbits corresponding to?
So I'm going to talk about that in a bit, but yeah, these things will grow essentially until they hit some kind of an innermost stable orbit.
So beyond it, there's no real solution.
That's right. Beyond that, you don't have stable orbits. You can still, write these things down, but you know that if you sneeze on a particle that's on that orbit, it is rapidly destabilized, and it will either be flung to infinity or plunged into a black hole.
So the frequency is imaginary or complex?
No, you can actually write down frequencies for those things there. It's just that if you look at how the potentials behave in that region, they're curved in such a way that it can't, you can put it on that thing, you can put it on an orbit. You know what, actually I'm wrong. Some of the frequencies can be characterized in that limit, but the radial frequency is not. And that is, in fact, going to be important for something I say in a moment. Yeah, so the radial frequency actually becomes imaginary in that case. And so if you have radial motion inside the, plunge. And I'll return to that point shortly. When I put all of these things together, sadly this video doesn't come out too well, but you get this sort of structure in which you have, because all the different frequencies are rather different from one another, body sort of moves slowly at large radius and then whirls around the black hole, coming back out at small radius to whirl back out again. And I really need to make a clearer version of that video. Okay, so that's how things look at the leading order in the mass ratio, the zeroth order in the mass ratio. Let's add my first corrections to this. So when I add the first corrections, I have one forcing term that is changing the evolution of the angles that set my coordinates, and another term here that says that my constants are no longer quite so constant. To begin seeing what effect these things have, I want to discuss an average form of these driving terms. Okay, so I'm going to imagine, what I really should be doing is defining an average with respect to time. I imagine that an orbit sort of lives for some long time, and then ask how does this behave as I average over long times. That turns out to be equivalent to doing an average with respect to two of my angles that characterize position. So I'm going to define my averaging with respect to the angles that characterize the theta and the arm motion like this.
Your lambda, what's that? Is that time?
This lambda is a time variable.
Okay.
Yeah, it's a time variable that I had on a previous slide, but I didn't call attention to it. Yeah, it's a time variable that's particularly convenient for Kerr black holes because it completely decouples the arm and theta motion, which is otherwise a bit nasty. Yeah. So when I average this forcing function up here, what you end up finding is that it's equivalent to just shifting these frequencies. Okay? So I can think of this as essentially saying that, remember that these things come from the interaction of the orbiting body with its own change to the spacetime. And so this is saying that there's a conservative effect, which is sort of equivalent to this thing changing its own orbital frequency somewhat. Okay? A very similar effect actually happens, there's actually a classic paper of this. This is a self-force effect. You see Dirac first worked this out for electromagnetic interaction in 1938. For a charge, you can think of this as you take an electron, you accelerate it, and its own field lines are back reacting on it. This is the gravitational equivalent of that. Okay? It's the space-time back reacting on the body and causing it to change its orbital frequencies with a correction proportional to the mass ratio. When I average the forcing function down here, that is describing how my orbital constants are changing as time goes on. And so this is a leading dissipative modification of binary's orbital dynamics. Essentially is what you expect from, say, gravitational wave emission carrying away energy and angular momentum, and something similar to angular momentum from the system.
So in the end, you get that by integrated by parts of the dipole formula.
Right.
Can you get a similar derivation for particle or formula?
You can. That's right. I'm going to talk about that in some more detail because for the key result that I'm going to talk about later, it comes from how you have to modify that when some of these resonances I talk about come about. So what I'm going to do to set up my discussion here is work in sort of an approximation to the true equation of motion, which I substitute the average form of these forcing terms in here. I'm going to argue as to why that is good, but I'm also going to highlight that one of the key things I want to talk about comes from when this averaging fails. I am actually, though, going to neglect this conservative term. there's a real issue of principle as to why we do this, in which one can show that this conservative term actually has a much smaller impact on the system than the dissipative one does. It's not negligible, and Eric Poisson and students and collaborators as well have actually argued quite eloquently that if you completely neglect it, you're making a big mistake. That's the argument in principle. In practice, I'm really doing this because we don't have to calculate it yet. And I have a rule that I try to only calculate things I know how to calculate. So,
what do you mean you don't know how to calculate that?
This is the self-force problem for a body moving in a curved space-time. Actually being able to calculate, so when you're back in Milwaukee, talk to John Friedman about this sometime. I've got an afternoon free. Actually computing the back reaction, or the self-interaction of a moving body in a curved space-time is not yet a solved problem. That's the end of it. It is solved for Schwarzschild, and I think people are close to doing it for Kerr, but it's a mess. And so even when it is working, I think we're probably going to be doing it in a somewhat kludgy way initially. Okay. To quantify my, in principle, why I neglect these things, when you actually calculate what impact this dissipative half term has on, for instance, say, the number of orbits that a binary spends in the frequency band of a detector, it scales as 1 over the mass ratio. Okay, so smaller the mass ratio, the more orbits are in bands. This thing changes that by a factor that's of order epsilon times the dissipative term. So you get some effect that sort of scales independent of mass ratio in your band. That's the cause of Eric Poisson arguing that we shouldn't neglect it entirely, but it's why, as a matter of principle, it's at least not as important as this thing. So I'm going to use what has been called the radiative approximation, where I'm basically treating the orbit as though it were geodesics on short time scale with constants describing each of those geodesics changing on some slower radiative time scale. Okay, so backing up, key to all this was how I defined this averaging, which you call it as essentially an averaging with respect to these angles that we use to define the motion.
So why are you averaging over 5?
I'm not averaging over 5 because thanks to the axisymmetry of the space-time, the forcing function is independent of it.
Okay.
So it comes
So
for
your
free.
bench system, you're already averaging.
Exactly. It comes for free. Yeah, so I only need to, the key to this is averaging behavior of these forcing functions. They depend on r and theta, but they're independent of phi and time. So it's a good question. It comes along for free, essentially. Now, for most Kerr orbits, this kind of an averaging turns out to be very accurate. I'll show you what I mean by very accurate in just a moment. The reason for this is that when I describe the geometry of a Kerr orbit, it's sort of, you think of it as a torus in the space near the black hole. It has a minimum radius, a maximum radius, and sort of a maximum and minimum angle. I've taken that sort of cross-section and blown it up here. Your typical orbit will actually ergodically fill that torus. You wait long enough, it will come arbitrarily close to every point within the torus. Right? This thing here, this is like actually a fairly poor example of an ergodic orbit, but it's one that kind of illustrates the point. I've allowed this particular set of parameters to go through 9 radial periods, and if I'd let it go through, say, 20, it would have come to within, on the scale of this box, sort of my finger length of every point within this torus.
But most of them, so there are Kerr orbits which are close then, right?
Let me explain, I'll explain the most in just a moment. Yes, that is put there to be provocative. So, because it comes close to most of these things, when I do an average like this, it means that a real physical orbit, essentially, even if I'm not doing the average, it comes close to every point that's accessible to it, and a real orbit effectively does this averaging operation anyway. And you can kind of see this. So this is sort of what the red line here, it kind of shows me what the instantaneous forcing term typically looks like. Sort of got small scale oscillations with some overall secular drift, and the average is the green that's plotted within this. Okay? So essentially the average gives me my overall secular effect, and there's short time scale oscillations which have some importance, but they're very subdominant. But as I put with that most, not all orbits are actually going to ergodically fill that torus. That happens when your two orbital frequencies, the theta and the r frequencies, happen to be a ratio of small integers. If that is the case, then your orbit does not ergodically fill its available space. It traces out some kind of a Lissajous figure within that torus. Here's one example of this. Okay, so in this one, I again let this thing go through, I think, 9 or 10 radial periods. And the thickness of this line is really determined by the thickness of the line that I drew in SuperMongo. When I actually look at the numerical data, it comes essentially back on top of itself to within, the accuracy of computing this ratio of frequencies.
Is there a simple way of seeing why this is a rectangle in the theta plane? At first sight, that seems miraculous.
It's actually not. I mean, this is just a coordinate representation of this thing here. I mean, it is okay.
Only one coordinate system.
That's right. That's right. But why is it that it goes? Is it in fact exactly in the Fourier linguistic way that it has a maximum theta and a minimum theta, minimum r and maximum r? I don't have a good answer to that. That it is. I think you're right. It is kind of miraculous, and that is just how Fourier linguist coordinates turn out to be a good one to describe these orbits. Yeah, I think so. I mean, Fourier linguist, it cleans up, it reduces the Schwarzschild in the right limit, but other than that, I don't have questions. Right. Point you making.
So is this true only if it's exactly a ratio of integers, or would it asymptotically approach this? Space if it was asymptotically.
Well, so let me state that the moment I'm talking just about orbits that last, I'm not taking into account any back reaction. Okay, I'm just looking at the geodesic orbits. Okay, so if this is exactly a ratio of integers, this is definitely the case. If it's not quite a ratio of integers, then it's how close it is will determine how long you have to wait before it ergodically fills things up. And that's actually a point it's related to some of my concluding thoughts about where we go with this work next. So right now, let's just imagine I'm exactly on a geodesic orbit. If I hit one of these things, I no longer fill up this the torus. My usual notion of torus averaging is going to fail. One thing that's particularly interesting when that happens is that the geometry of the Lissajous figure inside the torus becomes phase dependent. Okay, in other words, there's sort of an accidental phase, which you can think of as the theta angle at the moment the orbit passes through periapsis, which sets this geometry. So in this particular case, I've chosen my parameters, so I'm exactly on a 3-to-1 resonance, and at periapsis, my orbit passes through 90 degrees. The exact same orbital parameters, but I vary the phase so that the orbit is at theta min as it passes through periapsis, and I get a very different Lissajous figure. If I think about what this means in terms of the points that I pass through when I attempt to do my averaging, I'm sampling very different parts of this forcing function. I'm going to get different results. So another way to think about what is going on is the breakdown of my averaging here. We looked at sort of algebraically. If I take my forcing function, expand it in Fourier modes, for a typical non-resonant orbit, this will vanish for every k and n except for k and n equals 0. So k and n are just harmonics of the theta motion and the radial motion. So if I have a non-resonant orbit, when I average this thing over theta and q theta and qr, only the 0, 0 term survives the average. On a resonant orbit, though, I can find values of k and n such that there exist pairs where the exponential vanishes. I get all these additional terms that contribute to the sum. So my forcing function, when I average it, has very different behavior. What this means is that rather than these sort of small-scale oscillations washing out as I go through an inspiral, when I hit one of these resonances, various effects are combining in phase. So what will happen is, rather than just sort of continuing on my simple sector evolution, I get that resonance, boom, it's a big kick, and then maybe after it comes out of resonance, it tracks a different system. And in fact, as we've been looking at this more carefully, it looks like we can kind of define the system as having a nicely averaged motion at the beginning, some kind of a nicely averaged motion at the end. We just have to figure out how to compute the jump from one average track to another. What's a little scary is that how we actually jump from one to another has this sort of phase dependence associated with it. It makes the system a lot messier. What has been shown, and I'll talk about the results that show this, is that when you take into account the kicking of the system that's due to this resonance, your phasing is changed by a factor that is actually intermediate to the leading dissipative term and the conservative term. It comes in at a factor of the square root of the mass ratio times the leading term. And that ends up actually changing the number of orbits relative to a model that ignores the resonance by dozens to hundreds. much more serious effect than people had ever really seen before.
Does the epsilon to the half depends on which kind of resonance it is?
The numerical this epsilon to the half doesn't seem to, for the ones, at least all the ones that show up kind of forcing terms that come out of the general relativity analysis. The coefficient may vary. It's certainly going to vary though.
For quantum dynamics, it definitely depends on which resonance.
Yeah. We can talk about that some more afterwards. I suspect it has to do with just the form of that forcing term we're dealing with, because they are it's fairly universal, but it has parameter dependence in it. Max.
The number of such orbits that measure zero.
Yes.
Meaning there's infinitely more orbits.
Can I come back to that point?
This.
Exactly. Can I come back to that point in just a minute? Because I have a slide that addresses exactly that very soon, actually. And you're absolutely right. But remember, in an inspiral, you pass through a large sequence of these things. So let me just, one thought is that I think one way that may be useful to think about what's actually happening here is that it's kind of similar to what you have when a pulsar glitches. You know, we understand the system before the glitch, we understand the system after the glitch, and something weird kind of happens in the middle. If you just sort of think to yourself, well, I can model this, I can model that, there'd be dragons here. Perhaps you can imagine modeling the system that way, but we kind of need to understand how strong and how often those dragons actually bite. This is a point that I made, so I've been working on this project with Anna Flanagan, and it was a bit of a kick in the butt for him to realize that people have seen these kind of effects all the time in Newtonian gravity. All we're really seeing here is the same basic physics that has been known for a long time in a lot of Newtonian systems. So a cute example of this is, of course, the orbit of Mercury, which I believe today's physics colloquium is about. In this case, we have the spin and the orbital periods that are in a 3-to-2 resonance due to tidal locking. That is one where sort of what you're doing is including structure and gravitational interaction beyond the point mass, looking actually at tides and their effects on these bodies. If you have multi-body systems, you also get strong resonant effects just because you have different forces that can add with one another in phase. And the reason I bring this up is that this is the same basic physics as what I'm talking about here, in that what we're finding is that on resonance, effects that normally combine incoherently are no longer combining coherently. They actually go in phase and cause a dramatic change from what you get in the normal behavior. Okay, so crucial questions. Here's Max's question. How many resonances can actually occur? Max correctly pointed out this is a set of measure zero of the orbits that actually achieve this. Do we actually get them? And if we do, how big of a kick do you get at each one? Yeah.
Also, are these measure zero work as attractors or not?
Right. So that's exactly what I'm answering right now.
Okay.
Yeah. So the number of resonances that any inspiral is actually going to encounter en route to, so when one thinks about how an inspiral behaves, you start with some relatively large radius orbit. It shrinks due to gravitational radiation until you hit a separatrix between stable and unstable orbits. So this is, so if you remember your general relativity class, you learned that orbits of a Schwarzschild black hole are stable outside of r equals 6m. Now, generalize the spin, throw in dependence on orbital inclination and eccentricity, and you get this two-dimensional sheet in a plane of sort of orbital separation, inclination, and eccentricity. So your inspiral starts out here at large radius, comes in until it hits the separatrix at some point, and then the radial frequency becomes imaginary at that point, and it plunges into the large black hole. What we find is that on the separatrix, the radial frequency actually goes to zero. And so the ratio, omega theta to omega r, diverges, passing through every integer ratio on the way. Now, not all of these resonances are going to be equally important. As we approach the separatrix, they are going to become shorter-lived, and they're going to become more closely spaced. And so the real interesting question is, do we hit them sort of far enough out in the inspiral that we care about them? So my student at MIT, Teukolsky, and I have done just a really quick calculation to count up how often resonances matter. We use sort of a cheap version of the radiative approximation that we can code up on a laptop very quickly, and looked at a wide sample of small bodies plunging into Kerr black holes. So here's one particular example where I started with 1 solar mass body going to a 1 million solar mass black hole. This thing passes through the 3:2 orbital resonance with 15 months left before it hits the separatrix. It then passes through the 2:1 ratio with 2 months left, through the 3:1 resonance with 6 days left. We stopped counting at that point because they were starting to become fast and furious and we were less interested. These results were typical. What we found in doing our survey is that these resonances are generic. Every large mass ratio inspiral hits a couple of them in the year or so prior to hitting the separatrix. So even though they are a set of measure zero, because we pass through a large number of orbits en route from sort of initially seeing this thing to the final plunge, you typically, sort of hitting 2 or 3 en route to the final plunge turns out to be typical. There are then interesting questions about how important each one is, and that's what the remainder of this talk is and our work has been about. So concretely, we want to know how big of a kick does an inspiral experience when it hits one of these resonances. This was first done by Anna Flanagan and his former student Tanya Hinderer in a paper that was just published a couple months ago. They did it in kind of a clever cheat, where they used exact Kerr orbits to study the short timescale physics and post-Newtonian description of the forcing term. Okay? And what they found, so this is an example of what the system looks like as it, in this sort of exact analysis of the system, modulo the using post-Newtonian forces, as it went through the 3:2 orbital resonance. And we see, so this is showing what the orbital quantities that would be constant in the absence of the self-interaction, how they behave as you move along here relative to their unforced variant.
How does it work?
Say it again?
How does it work for a post-Newtonian description to get all the resonant interaction?
So you get that because you are treating the orbits exactly. Okay? It's just a forcing term that you're treating in a post-Newtonian way, which is a cheat. I'm going to come to that in a moment. Okay? That is actually the biggest concern with this. So what they basically confirm this cartoon I sketched earlier, where you sort of have a really simple to understand behavior early on. When you hit the resonance, things kind of go crazy, and then you fall into another easy to understand track afterwards. You ask yourself, well, okay, that's great. You get kicked on this new thing. How does that actually change the evolution of the system? So this is the shift in orbital phase relative to a model that does not take into account the resonance. And they find, so this is the shift in phase divided by 2 pi, changes by hundreds of radians. That is a very large effect. So this made a lot of people sort of go, whoa, why have we never looked at this effect before? Okay, this is something that's been hidden in all of the analyses, but it's never really come out. Well, one issue is that they're using post-Newtonian forcing terms. This is an expansion essentially away from the Newtonian potential. And when you're doing that for a very strong field orbit of a Kerr black hole, you deserve to be spanked a little bit. Okay, that's really not the right thing to do. It's a good way to start the analysis, but you've got to do something a little bit better. So for the remainder of the talk, I'm going to talk about the results we found doing an analysis that works well all the way into the strong field. So the key thing which, as I've already emphasized, what's going on here is that we've typically computed inspirals using this kind of an averaging notion for our forcing term. And when we're on a resonance, that averaging fails. What we can do is replace it with another version of the averaging that is correct. So rather than having these two angles, q theta and qr, that are completely separate from one another, imagine that you are moving along a trajectory where your theta motion is a simple function of the r motion, and this sort of offset accidental phase. So mathematically, I'm going to do an analysis where I've replaced my forcing term with something that looks like this. Let me talk a little bit about how I'm going to actually compute my things here. So the strong field formalism I'm going to use is based on the Teukolsky equation, which is a perturbation formalism for computing gravitational radiation and other curvature quantities on the background of a Kerr black hole. So for our purposes, the key thing that matter is that there's a few bits that you have to compute numerically. The angular dependence turns out to be pretty simple to compute. And there's an amplitude, which is a little more of a challenge to compute, but not too difficult. When you actually go through and work this out, you find that this amplitude depends directly on this accidental phase parameter. So there's this chi0 here, essentially sets the value of the orbit's theta as it passes through periapsis. So relative to some fiducial angle where I set that to 0, it's going to pick up a phase function that looks like this. Turns out that I can do something similar. This describes the radiation at infinity. There's another contribution, which is due to coupling, tidal coupling to the black hole. I can also get that, but the math is messy, so I'm going to skip it. Punchline is that quantity like this gives me everything I'm going to need to know. Okay, so once I actually have this thing, it's a very simple matter to extract how the energy and the angular momentum change. This here is just for non-resonant orbits. Notice what enters into this thing is the modulus squared of these amplitudes. All that information about the phase has gone away. So for non-resonant orbits, we don't care that, at least computing the inspiral, we don't care what the phase is when this thing passes through periapsis. The quantity that Phil was asking about, this Q, this Carter constant, it's a little bit more of a mess, but there's sort of a miracle that happens, and it turns out it also can be computed using just knowledge of these curvature quantities that I can compute. It takes a sort of really interesting form in which it just looks like distant radiation times quantities that are local to the orbit. Or it depends. So this upsilon here is essentially my theta frequency, but conjugate to this lambda time that I was discussing. Okay, how does this change when I go from non-resonant to resonant? So in all of this, my mode frequency is just harmonics of the three fundamental frequencies. As I enter a resonance, two of these frequencies become degenerate quanta. Okay, they're related by some simple ratio of integers. And so what this means is that two of my harmonic indices lose meaning. They get sort of subsumed into one. What this is telling us that when I'm on a resonance, I'm going to characterize my different modes by a bunch of harmonic indices. And every resonant index actually corresponds to an infinite set of pairs of modes that I would have calculated in the non-resonant case that are compatible with this relation. And I think this is kind of key to seeing what happens, why I get some of these phase-dependent effects, kicks, when I enter a resonance. So let's imagine that as I'm entering a resonance, I have a large number of, every one of these lines that I've drawn here represents one of the amplitudes of my radiation field. So as I am approaching my resonance, so these things are close to but not exactly at yet the 3-to-2 resonance, the lines associated with my radiation field are completely separated from one another. I spiral in a little bit and they come close together. I hit exactly the resonance, and all 5 of these lines merge into one single line. And then they come out of it, they split again. What's important here is that the actual magnitude of the line when they come together and merge on the resonance depends on this accidental phase. So here is one example of a Lissajous figure for the orbit for a 3-to-2 resonance, where when my lines merge, I get a particularly large amplitude for my radiation field. Exact same orbital parameters, but a different phase, they come together and I get a much smaller amplitude. So all of a sudden this accidental parameter has become physically very important. Where this is going to actually enter into my analysis is that my amplitude coefficients on resonance can be sort of subsumed into a grand resonant amplitude that looks like this. I'm going to leave the dependence on amplitude explicitly in there. Once I have that, I can sort of look at it and see, well, how does it actually vary? In fact, you realize this isn't such a great plot. This is the one that has sort of the most interesting information. So this is the modulus of one of the amplitude of one of my radiation harmonics, exactly on a resonance. If I were off resonance, this would be a flat line. But on resonance, I have this strong dependence on the phase, and this thing varies by about 20% from peak to trough. That's actually a fairly small variation among the different cases that I've studied. Can then take this thing, generalize my formulas for how the energy and the angular momentum evolve. With a little bit of work, you can do the same thing for the rate of change of the Carter constant. Don't worry about the details here. The key thing is that it's completely understood at this point.
So,
yes?
Well, maybe you should show the results and I'll ask the question.
Yeah, okay. Well, I'm now getting into results. Yeah.
Well, but the basic question of principle here.
Yeah.
I mean, it's not this equation. You're looking at resonance in theta and R motions.
Right.
And so somehow the non-planarity of the orbit is important.
Yes.
Now, obviously, in an inspiral, and this would hold for more general mass distribution, say, just in the weak field limit,
Right.
which defines the particle formula, you can imagine the resonance between the R frequency and phi frequency.
Right.
But non-one-to-one.
Right.
But if you did consider that case, so it's a non-point mass distribution, would you get any mass radiation in this little field limit, or do you really?
You might actually. I mean, at the end of this talk, actually, I have a couple ideas for where we might look for other kinds of resonances. That's one I hadn't thought of, but yeah, and I think
it's simpler, in fact.
It might be, yeah. This kind of grew out of work people have been doing on cell force analyses, which is how we went into this.
Well, but the same question still arises, though. You still have your phi frequency, you make use of axis symmetry.
Sure. Well, in this case, you have kind of a mass distribution. You might lose the axis symmetry, the kind of distribution you're talking about.
Well, but here you don't seem to be picking out any effect of resonances between the phi frequency and the R frequency, the phi frequency and the theta. It's only being on theta.
It's only between R and theta, and that is because for the particular model I'm looking at, the forcing terms that matter here don't have any dependence on phi. Okay? That's really all that it's coming down to. There's nothing deep there. It's just that because this thing is, it's a forcing. Exactly. So, if you have an interaction where there is some azimuthal dependence link, then I think you go back to the drawing board. Yes, you may have something like that. And in fact, I'm going to talk a little bit at the end here about a case where I think you may see something like that. And I think there may be room to explore some of the stuff in more general systems. Anyway, so let me just go through and give you a little bit of a catalog of some of the results that we have actually seen. So if I look at how much energy is radiated in a particular mode, I actually see it sort of varying with respect to my phase parameter by a factor of 3 from minimum to maximum. Okay, so on this particular mode, when this accidental phase parameter is of order 2 radians, this particular set of harmonic indices radiates 3 times as much than it does when that set of harmonics, when that accidental phase is equal to 5 radians. Okay, very strong variation, quite surprising to me. One reason that I've been talking about this Carter constant a little bit is it turns out to have some of the most surprising behavior. Recall in the non-resonant case, all of these fluxes depended on the modulus squared of something. Here, because of all the complicated phase interactions that are coming together, here's a quantity that in the non-resonant case must be positive definite, actually becomes negative over a certain region of accessible phase space, dramatically changing the possible evolution of the system. So when I show you these results and the way some of these fluxes evolve, I'm just looking at individual modes. When you sum a lot of them together, which is what you have to do to get the net evolution of the system, a lot of variation washes away. So in this particular case I'm seeing, the energy flux to infinity varies by less than 1%. It's about 0.2%. And the flux that's absorbed by the black hole varies by about 7%. This ends up being sort of on the high end of typical for the kind of rates of change that we've seen in all these kind of quantities. So that seems a lot smaller, and you sort of think, okay, well maybe this isn't going to be quite such a big effect. However, this turns out to be pretty much dead-on consistent with what the Flanagan Hinderer model predicted using a simple post-Newtonian case. So when we got a 0.2% change in, for example, the energy flux, these guys found that that ended up changing the phasing of the system by a couple hundred radians. So we are completely consistent with this, which is suggesting to us that even when we're putting in the correct strong field physics, we are in fact going to see resonances affecting the evolution of systems at the sort of dozens to hundreds of radians effects. But I have a cautionary note, which is that at the moment, the code that we've developed for this can only compute quantities that are exactly on the resonance. This is not enough for us to assess how big of an effect we would have as we do a full inspiral and evolve all the way through a resonance. So what we need to be able to do is look at how the resonance, how the sort of resonant combination of modes, how it is set up, we understand it right at the peak, and then how it comes out again as we exit the resonance. I'd sort of say intuitively, we've now computed the height of each resonance, but we don't know the width. That is what we are gearing up to do next. I would say the key point to bear in mind, if I come back to this picture,
What do we decide on this time to study the resonance?
It's exactly what I'm going to talk about. That is exactly this point. Yes, that's exactly right. That is the key point. So when we've done this analysis so far, because we sort of ignored back reaction and doing this kind of thing, when I look at my radiation field, it really looks like a whole bunch of lines. Okay, but in fact, the system is spiraling in, the frequencies are changing, and they are not lines, they actually have some width associated with them. So what we need to do is generalize our analysis to understand how to compute the radiation field for an evolving system. And then what we'll know is that the averaging is beginning to fail when sort of fat lines like this come into contact with one another. And then your normal averaging is, again, sort of effective when they cease to be in contact as it passes through. So what we are gearing up to do next is take the codes we developed to look at the self-interaction of this thing here without the averaging that we are doing at the moment. Okay, what we want to do is actually couple an instantaneous computation of the dissipative self-force to a real inspiral, and then assess the kick, really look at what happens to the kick of these parameters as we evolve through one of these resonances, knowing that we go through several en route to the final plunge. So what I hope I've convinced you is that to me, it's a surprise that we missed this before. Okay, strong field orbits of Kerr black holes, simply looking at just point particle orbits, becomes clear that you have the perfect venue for developing orbital resonances. It's just like in Newtonian physics. Essentially, all that happens when you go through a resonance is that various forces, which are normally incoherent, combine in phase. This has been neglected by a surprising number of previous analyses, and I think can have a large effect. An example, though, something which we have not concluded, and this gets to some of the points Chris was just raising with me. Having raised this point, I think we should begin thinking about other cases where this may end up happening. One of the ones that I think might be interesting from the standpoint of numerical relativity is what if your inspiraling body has more structure than just sort of a point-like mass? And we know in the large mass ratio limit that in this case, the body's spin couples to space-time curvature. The spin's going to precess, and there is a spin curvature force that arises from the coupling of the spin to the curvature tensor of the background body. The precession associated with the spin has some kind of a frequency associated with it. I think what we'll find is, again, there will generically be moments in which the precession frequency falls into some kind of a resonance with aspects of the orbit. And we're going to then find that this spin curvature force, which in general, when we look at it, is kind of a small wiggly overlay on an overall evolution of the system. It won't be that way. I think we can again get sort of large kicks. And in this case, I think this is an example of where I think having the phi dependence built into this, that may be something where, depending on the accidental geometry of the system, you'll have a dependence on your axial angle, and it can become a lot more complicated. And that was shorter than I thought it would. I will end there.
So if you started at large radii,
yeah,
then all frequencies, there's only one frequency, which
right.
is they're all the same. So J,
yeah,
all the same. So you start off in a fully resonant regime, even far away, and then as you go in, first of all, the orbit circular, as they go in.
It does, but if you start out, so the kind of systems that we are thinking about are ones that are formed through capture processes. So
you start from the random position in phase space.
You start from some random position phases, typically with a very large eccentricity, so that by the time it encounters the separators and plunge, it has reduced its eccentricity, but it's only reduced it to say 0.2 or 0.3.
So you expect a random orbit to enter at a random point in the action phase.
Yeah. Yeah.
And then if you say, in the grand scheme of things, sure, there are certain steps where things happen, and then final number, the takeaway is that if we just ignore all of these things, you're still good to 7% or something, or 2%.
You're still good to a few percent, but that few percent is not enough to give a phase coherent model of the system, which is what people are after for a lot of these analyses.
But phase coherent means is a final, phase in which you fall into the black hole relative to the position you started off with. In between, you may have millions of orbits.
Right.
So you're really only off by a part of a billion, maybe, which may be a lot of radians, but it's really a tiny effect.
Well, it depends on what you want to do, right? I mean, if your goal is actually to track this thing, now think about when you're measuring the phase of a pulsar. If you're off by a part in a billion and you measure a trillion, a trillion spins on the axis, you're very off. This is essentially trying to do the same thing.
If you detect it for that whole range, right?
That's right.
If you actually saw it as far out and it followed all the way to the cloud.
Well, so the point we're making with this is that specifically in the context of the kind of, so what motivated this originally we're trying to measure these large mass ratio systems with the space-phase detectors. I mean, LITA is one of the original motivations. It's not on the drawing board anymore, but it still gives us some kind of a strawman framework to ask questions like this. And so in that case, you're looking at measuring what you want to do with these things, to be able to track them over, say, 10,000 to 100,000 orbits. Okay? And so if you're off by 1%, 1% of 10,000 is 100 orbits, that's enough to completely lose phase and to lose the science that you want to get out of this. That was one of the original motivators for this. Now I'm kind of hoping to take us in a bit of a different direction, because I think that what may even be more interesting with this is trying to explore and see if we find similar resonant effects in more general systems. But in the meantime, this sort of original motivation gave it kind of a nice toy box to begin exploring some of this physics and to see where in the radiation reaction force framework resonant effects have an influence.
You always get that in any non-axisymmetric system. I mean, imagine I have a star going, or Milky Way going on the galactic plane.
Sure. Well, that was kind of my point about bringing up the, comparing it with Newtonian resonances. Okay, I mean, this is generic behavior, and which is why, I kind of feel like it's a bit of a shame that we hadn't recognized that these kind of resonances might play a role in relativistic systems previously. Okay. At the end of the day, then the question becomes, how often do you encounter them? How important are they when they actually occur? And that's where I think there's some room to explore and see what's going on.
Scott, so it's not totally true that you have to do the basic average over the 5 in order to get the dissipated force on at least on the action variable.
That's right, yes.
Okay. Right, and the other thing is that, so I guess I haven't appreciated this, like for MRIs, when people were trying to detect the way they were trying to do it was basically temperature matching, right?
Well, the question, let me back up. I would say that is the gold standard.
Okay.
Okay, and so then the question becomes, can you achieve that gold standard? And if not, is there some silver standard that you might want to relax your goals to and try to achieve? And one of the things that I think has come out of this is this kind of, unless you can actually figure out a way to coherently model the system as it goes through one of these resonances, I think the thing to do is to actually take the point of view that it's probably going to look something like a glitching pulsar. And imagine trying to track the system up to a resonance, and then look for it again afterwards, and track it after the resonance. Next thing, you had your hand up for a bit.
So you can have a black hole and massive gas.
Yeah.
One might expect that these resonances will disturb the orbits strongly. So how about a collective type of Landauer resonance now?
Okay. I have not thought about that, but this, we go back to where I look at these orbital frequencies. This is what you have to play with, is some kind of a structure like this. This is for a particular set of orbital parameters, but you can imagine, if you're in some strong field region and you have a collection of particles that are, moving around near there, you can always calculate frequencies associated with different degrees of freedom of their motion. And, there surely will be, if you move deep enough in a strong field, regions of the phase space where resonant effects can be found. And then it becomes an interesting question to ask, what can you do with them? Are the wheels turning? It looks like yours. Wait, you have your
And I would say potential, or if you have at any degree of freedom, like a spin of a black hole, there's no reason that these systems are integrable, so you may not have angle of action.
That's right.
In which case, your life gets even easier because you're guaranteed to fill your volume now.
Exactly. Yeah, in some sense, this whole effect comes about because of, this. Because Kerr orbits have this third integral. It's because of this sort of magic of the third integral, which means that you do have these three well-defined frequencies associated with it. And in general, as you say, in general potential, you won't have that. And the more general result you would expect is, at a minimum, ergodically filling your accessible region, or possibly even chaotic motion. Yeah, and in that case, you're never going to. presumably if you were in that limit, you probably should be doing a much more basic I mean, this is, a lot of things have been adapted to the fact that you have this sort of beautiful, all these nice effects happen for Kerr, which don't happen in general.
Like if you took a charge put, is the interval still exist?
I believe it does. I have to go back and check the textbooks on that, but yeah, I believe so. Yeah, I mean, it turns out that the existence of this thing is related to the fact that, in fact, I know it does, because the Kerr-Maxwell solution has, in addition to the normal killing vectors associated with time symmetry and axisymmetry, there's a killing tensor, which doesn't have any really simple geometric interpretation associated with it, which is associated with that. And I think that it exists for charged black holes as well. Black holes are magic. Yeah.
Is there any plausible way you could do something like this in a numerical relativity?
That's what I wanted to ask you guys about. So, this is, that's one of the reasons why. So, one of the things I'll be doing next when I finish up our current analysis with Aina, Tanya, and my student is begin exploring what happens in the large mass ratio limit when we include the spring curvature term. Because in that case, we can calculate precession frequencies associated with this thing, more or less analytically, or analytically up to a couple of numerical integrals. And then it becomes not too difficult to sort of hunt through our phase space and try to find places where it resonates. And I think it'll be really interesting to see whether, in that case, you in fact do see that the spin curvature terms combine kind of in phase the way we saw here and kick the system in a surprising way. I would wonder, I mean, I think we should do sort of the large mass ratio limit of this, where we can do it quasi-analytically first to give you guys an idea where to explore. But I would think that, what is, all these effects we found kind of have this scaling where, it's reduced by the square root of the mass ratio. And so, if we have mass ratios that are just kissing what numerical relativity can handle, 20 to 1, something like that, are these effects important in there? I think that's another interesting question. At what mass ratio can you cease? Can you stop worrying about this?
I think people have found before that self-force gives surprisingly good answers when you use the symmetric mass ratio than the mass ratio.
Exactly. So, but we haven't quite, this is fresh off the presses essentially, and we haven't gone through and sort of explored yet, when we sort of find that the orbital phasing effects are hundreds of radians, it's at a mass ratio of 10 to the 6. Okay, so that sort of suggests if we go down to, mass ratio of 10 to the 3, it might be down to 10 radian effect or something like that. I'm curious, at what point do we get to a mass ratio where you can imagine starting to explore it? I really think that going to something like looking at spin coupling effects is where you're likely to see something that's more interesting. But you still probably have to go to the largest mass ratio, and I'm not sure where would be a good place to sort of touch base with the numerical calculations yet.
Is this spin coupling for black holes or just things that have structure?
So this is, where this comes from is if you enforce conservation of the stress energy tensor, that equals 0. All you are doing is asserting that your body has some dipole moment associated with it, which is equivalent to a spin. Okay? But it's neglecting anything higher than that. So for instance, if you have like a neutron star, it'll also have a quadrupole moment, and there'll be an additional term in here related to the quadrupole moment coupling into it. I'm neglecting that in this analysis. So, this is the leading Dixon-Papapetrou forcing term, and it is generic for a spinning body. Works best with black holes.
I think we can continue the discussion over the cookies upstairs. Thanks for the video.